Quicksort is an efficient sorting algorithm, serving as a systematic method for placing the elements of an array in order. Developed by Tony Hoare in 1959, with his work published in 1961, it is still a commonly used algorithm for sorting. When implemented well, it can be about 2 or 3 times faster than its main competitors, merge sort and heap sort. Quicksort is a comparison sort, meaning that it can sort items of any type for which a less than relation is defined. In efficient implementations, it is not a stable sort, meaning that the relative order of equal sort items is not preserved. Quicksort can operate in place on an array, requiring small additional amounts of memory to perform the sorting. Mathematical analysis of Quicksort shows that, on average, the algorithm takes O comparisons to sort n items. In the worst case, it makes O comparisons, though this behavior is rare. History. The Quicksort algorithm was developed in 1959 by Tony Hoare while in the Soviet Union, as a visiting student at Moscow State University. At that time, Hoare worked in a project on machine translation for the National Physical Laboratory. As a part of translation process, he needed to sort the words of Russian sentences prior to looking them up in a Russian-English dictionary which was already sorted in alphabetic order on magnetic tape. After recognizing that his first idea, insertion sort, would be slow, he quickly came up with a new idea that was Quicksort. He wrote a program in Mercury autocode for the partition but couldn't write the program to account for the list of unsorted segments. On return to England, he was asked to write code for shell sort as part of his new job. Hoare mentioned to his boss that he knew of a faster algorithm and his boss bet sixpence that he didn't. His boss ultimately accepted that he had lost the bet. Later, Hoare learned about ALGOL and its ability to do recursion, which enabled him to publish the code in ACM. Quicksort gained widespread adoption, appearing, for example, in Unix as the default library sort function. Hence, it lent its name to the C standard library function Quicksort and in the reference implementation of Java. Robert Sedgwick's Ph.D. thesis in 1975 is considered a milestone in the study of Quicksort, where he resolved many open problems related to the analysis of various pivot selection schemes including sample sort, adaptive partitioning by Van Emden, as well as derivation of expected number of comparisons and swaps. Bentley and McIlroy incorporated various improvements for use in programming libraries, including a technique to deal with equal elements and a pivot scheme known as pseudo-median of 9, where a sample of 9 elements is divided into groups of 3 and then the median of the 3 medians from 3 groups is chosen. John Bentley described another simpler and compact partitioning scheme in his book Programming Pearls that he attributed to Niccolò Muto. Later Bentley wrote that he used Hoare's version for years but never really understood it, but Muto's version was simple enough to prove correct. Bentley described Quicksort as the most beautiful code I had ever written. In the same essay, Muto's partition scheme was also popularized by the textbook Introduction to Algorithms, although it is inferior to Hoare's scheme because it does 3 times more swaps on average and degrades to O runtime when all elements are equal. In 2009, Yaroslavsky proposed the new dual-pivot Quicksort implementation. In the Java core library mailing lists, he initiated a discussion claiming his new algorithm to be superior to the runtime library's sorting method, which was at that time based on the widely used and carefully tuned variant of classic Quicksort by Bentley and McIlroy. Yaroslavsky's Quicksort has been chosen as the new default sorting algorithm in Oracle's Java 7 runtime library after extensive empirical performance tests. Algorithm. Quicksort is a divide-and-conquer algorithm. Quicksort first divides a large array into 2 smaller sub-arrays, the low elements and the high elements. Quicksort can then recursively sort the sub-arrays. The steps are: pick an element, called a pivot, from the array. Partitioning. Reorder the array so that all elements with values less than the pivot come before the pivot, while all elements with values greater than the pivot come after it. After this partitioning, the pivot is in its final position. This is called the partition operation. Recursively apply the above steps to the subarray of elements with smaller values and separately to the subarray of elements with greater values. The base case of the recursion is arrays of size 0 or 1, which never need to be sorted. The pivot selection and partitioning steps can be done in several different ways. The choice of specific implementation schemes greatly affects the algorithm's performance. Low-Muto partition scheme. This scheme is attributed to Niccolo Muto and popularized by Bentley in his book Programming Pearls and Cormen et al. In their book Introduction to Algorithms. This scheme chooses a pivot which is typically the last element in the array. The algorithm maintains the index to put the pivot in variable I and each time when it finds an element less than or equal to pivot, this index is incremented and that element would be placed before the pivot. As this scheme is more compact and easy to understand, it is frequently used in introductory material, although it is less efficient than Hoare's original scheme. This scheme degrades to O when the array is already sorted as well as when the array has all equal elements. There have been various variants proposed to boost performance, including various ways to select pivot, deal with equal elements, use other sorting algorithms such as insertion sort for small arrays and so on. In pseudocode, a quicksort that sorts elements low through high of an array A can be expressed as algorithm quicksort is if low less than high then P equals partition quicksort. Quicksort algorithm partition is pivot equals A, high I equals low, place for swapping for J equals low to high 1. Do if A, J, pivot then swap A, I with A, J, I equals I plus 1. Swap A, I with A, high, return I. Sorting the entire array is accomplished by quicksort. Hoare partition scheme. The original partition scheme described by Car. Hoare uses two indices that start at the ends of the array being partitioned, then move toward each other, until they detect an inversion. A pair of elements, one greater than the pivot, one smaller, that are in the wrong order relative to each other. The inverted elements are then swapped. When the indices meet, the algorithm stops and returns the final index. There are many variants of this algorithm, for example, selecting pivot from A, high, instead of A, low. Hoare's scheme is more efficient than Low-Muto's partition scheme because it does 3 times fewer swaps on average, and it creates efficient partitions even when all values are equal. Like Low-Muto's partition scheme, Hoare partitioning also causes quicksort to degrade to O when the input array is already sorted. It also doesn't produce a stable sort. Note that in this scheme, the pivot's final location is not necessarily at the index that was returned, and the next 2 segments that the main algorithm recurs on are low P and an is if low less than high then P equals partition quicksort. Quicksort algorithm. Partition is pivot equals A, low I equals low 1, J equals high plus 1. Loop forever. Do J equals J1 while A, J greater than pivot. Do I equals I plus 1 while A, I less than pivot. If I less than J then swap A, I with A, J, else return J. Implementation issues. Choice of pivot. In the very early versions of quicksort, the leftmost element of the partition would often be chosen as the pivot element. Unfortunately, this causes worst-case behavior on already sorted arrays, which is a rather common use case. The problem was easily solved by choosing either a random index for the pivot, choosing the middle index of the partition, or choosing the median of the first, middle and last element of the partition for the pivot. This median of 3 rule counters the case of sorted input, and gives a better estimate of the optimal pivot than selecting any single element. when no information about the ordering of the input is known. Specifically, the expected number of comparisons needed to sort n elements with random pivot selection is 1.386 n log n. Median of 3 pivoting brings this down to Cn to 1.188 n log n, at the expense of a 3% increase in the expected number of swaps. An even stronger pivoting rule, for larger arrays, is to pick the ninth-er, a recursive median of 3, defined as ninth-er equals median of 3. Median of 3. Selecting a pivot element is also complicated by the existence of integer overflow. If the boundary indices of the subarray being sorted are sufficiently large, the naive expression for the middle index, 2, will cause overflow and provide an invalid pivot index. This can be overcome by using, for example, low +2 to index the middle element, at the cost of more complex arithmetic. Similar issues arise in some other methods of selecting the pivot element. Repeated elements with a partitioning algorithm such as the ones described above. Quicksort exhibits poor performance for inputs that contain many repeated elements. The problem is clearly apparent when all the input elements are equal. At each recursion, the left partition is empty, and the right partition has only decreased by one element. Consequently, the algorithm takes quadratic time to sort an array of equal values. To solve this problem, an alternative linear time partition routine can be used that separates the values into 3 groups. Values less than the pivot, values equal to the pivot, and values greater than the pivot. The values equal to the pivot are already sorted, so only the less than and greater than partitions need to be recursively sorted. In pseudocode, the quicksort algorithm becomes algorithm quicksort is if low less than high then p equals pivot left right equals partition. Note: multiple return values quicksort. The best case for the algorithm now occurs when all elements are equal. Optimizations. 2 other important optimizations, also suggested by Sedgwick and widely used in practice, are to make sure at most O space is used, recurse first into the smaller side of the partition, then use a tail call to recurse into the other. When the number of elements is below some threshold, switch to a non-recursive sorting algorithm such as insertion sort that performs fewer swaps, comparisons or other operations on such small arrays. An older variant of the previous optimization. When the number of elements is less than a threshold k, simply stop, then after the whole array has been processed, perform insertion sort on it. Stopping the recursion early leaves the array k sorted, meaning that each element is at most k positions away from its final sorted position. In this case, insertion sort takes O time to finish the sort, which is linear if k is a constant. Compared to the many small sorts optimization, this has the downside of wasting effort comparing keys across the many segment boundaries, and makes suboptimal use of cache memories. Parallelization. Quicksort's divide and conquer formulation makes it amenable to parallelization using task parallelism. The partitioning step is accomplished through the use of a parallel prefix sum algorithm to compute an index for each array element in its section of the partitioned array. Given an array of size n, the partitioning step performs O work in no time and requires O additional scratch space. After the array has been partitioned, the 2 partitions can be sorted recursively in parallel. Assuming an ideal choice of pivots, parallel quicksort sorts an array of size n in O work in no time using O additional space. Quicksort has some disadvantages when compared to alternative sorting algorithms, like merge sort, which complicate its efficient parallelization. The depth of Quicksort's divide and conquer tree directly impacts the algorithm's scalability, and this depth is highly dependent on the algorithm's choice of pivot. Additionally, it is difficult to parallelize the partitioning step efficiently in place. The use of scratch space simplifies the partitioning step, but increases the algorithm's memory footprint and constant overheads. Other more sophisticated parallel sorting algorithms can achieve even better time bounds. For example, in 1991 David Powers described a parallelized quicksort that can operate in no time on a CRCW pram with N processes by performing partitioning implicitly.